Okay, so it's a little bit confusing because regression analyses can refer to regressions and correlations. Generally, when I talk about regression, I mean a regression, and when I talk about a correlation, I'll say correlation, because it is confusing that they're both technically regressions. But I just want to make that clear in these next couple of slides that when it says regression analyses, it's referring to both of them as a group, or regression as like an umbrella term for them both. So when we're doing regression analyses, we're interested in finding an equation that describes the relationship between two continuous variables. So that's key, and that's what's really different from everything else that we've done. We have two continuous columns of data, and they're not the same numbers. If they were two continuous columns of numbers, but they were from the same units, that might signal to you that you're doing a t-test. You're comparing the means between two groups. If it was one column of categorical data and another column of continuous data, that would be a one-factor ANOVA. Two columns of two continuous variables that are different from each other would signal to you that it's a regression analysis. So a regression is different from a correlation in that we control the independent or explanatory variable. Because we controlled the independent variable, we can actually suggest causation. We can say, I changed X at equal intervals, and I saw this change in Y. Therefore, this change in X causes this change in Y. When we do a correlation, we can't control either of the variables. We're just observing and collecting data. Because of this, we cannot suggest causation, only demonstrate that there is a non-random relationship or association between the two variables. So that's the key difference, is that regressions are experimental and correlations are observational. Both of them are calculated the same way, but the inferences are very, very different from each other, the way that you interpret the results. So we, again, do these regressions for a couple of reasons. We want to generate a predictive equation describing the relationship between X and Y. We want to calculate descriptive stats that convey the strength of the relationship or the variation and dispersion between the points and between X and Y, and to demonstrate causality, specifically if we're doing a regression and not a correlation. There are a couple assumptions about these tests, just like with all other tests we've done. So we assume that the relationship between the dependent variable and the independent variable is linear. This is really important. If we don't think that A or X and Y are linear, there's no reason to make a linear model. So let's say we've got this axis and we've got points that look like this, right? That's a pretty clear linear relationship. And we would probably get a significant p-value saying like, yes, X and Y have a significant linear non-zero relationship. But let's say our points look like, let's see. Actually, I'm gonna change this to look like that. If we try to draw a straight line through this data, it'd probably be something like this. And we would get a p-value that's greater than 0.05. Our p-value would probably be like 1, meaning there is no significant non-zero, like the slope of the line is 0. There is no significant relationship between X and Y, no significant linear relationship between X and Y. But if we look at this data, we can kind of clearly see that there's a pattern to it, that there might be a relationship between X and Y, and that A line that might better fit it is a parabola. So even though there's a relationship between x and y, it's nonlinear. And as a result, a linear model is going to tell us that there is no significant relationship between x and y. That's why it's really important that before we do our tests, we have to have some idea or reason to believe that x and y are linear. And sometimes when you graph your data, you'll see a nonlinear pattern, and then you're like, well, maybe a linear model is not the best choice. Okay. We also assume that the values of the independent variables are fixed by the experimenter if we're doing a regression. This isn't true for correlation. The variation is in the dependent variable is normally distributed around the predicted variables or the predicted values. And what we mean by that is, let's say we got this line again, we got x, we got y, and we've got some points, right? This would be normally distributed around this line, right? The points kind of go from like this area to this area. If our points were like we would probably still get a line like this right through the center, but now we have this weird like disarray of like non-normal distributions around our line. So that's just what that's referring to. Again, not something, a lot of this stuff I'm not going to test you on, but I know that sometimes these words are just words and they don't really mean much. So hopefully that makes it make a little bit more sense. We also assume that the variances of y at each value of x are the same. So that kind of goes back to the figure I just showed you again. We want our numbers to be normally distributed and have equal variances at each of those values of our line. And lastly, that each observation, each x and y pair is independent of all the others. And sometimes these assumptions are often violated, but we're not going to worry about that in this class. So how do we actually do these? The first thing you want to do is plot the data. So what does the data look like? If the data isn't linear, a regression or correlation probably isn't the right choice unless you transform the data first. Next, you want to calculate sample statistics as estimates of the population parameters and test the hypothesis about the slope of the regression line or the correlation coefficient. And then make a confidence interval for the regression line. We're not going to be doing that in this class, and I'm not going to test you on it for your exam coming up. So when we do our regressions, our model 1 regression, we want to estimate the equation for the best fitting line or line of best fit that describes how the dependent variable changes as the independent variable changes, as we change the independent variable, really. And the equation for that is this y hat I equals a plus bx sub I, where a is the y-intercept, b is the slope, x sub I is the independent variable, y sub I is the dependent variable, and I is the index. And this is the same thing as y equals mx plus b, or this y equals beta sub 0, or beta naught plus beta sub 1 xi. These are all the same things. I believe that in our markdown, I refer to this y equals mx plus b equation. But when you see the hypotheses written, I'm referring to this beta 1 or b. So just a note there. When I'm talking about the slope, I'll be referring to it as b or beta 1. Beta 1 for the population, right? Remember we use Greek letters for population and like alphabetical letters for sample statistics. But it gets kind of confusing because there's a b in the y equals mx plus b equation and a b in the this one. But when I say b, I'm referring to the slope. So typically, our null hypothesis is that the slope of the line is 0, meaning the independent variable has no impact on the dependent variable, right? If we have data that looks like this, for each variable or each value of x, y is about the same. So x doesn't really have an impact on y. So when we write our hypotheses, our null hypothesis is that beta sub 1 or b, beta sub 1 or b, I'll accept either, equals 0. So the slope at the population or sample level is equal to 0. Therefore, the alternative is usually that there is some relationship between the variables. And that's just that the alternative then is that beta 1 or b does not equal 0. The slope is not 0. It's either bigger than 0 or less than 0. When we calculate these lines of best fit, and the slope and all of that stuff, we technically do that using more sum of squares. And we use something called a sum of cross products when we're doing linear regressions. And that can be written as SP, so sum of products XY, or SCP for sum of cross products. And it's literally just the product of the difference between each X or Y value and its mean. So comparing each X to the mean of X, each Y to the mean of Y, summing those two differences together, or sorry, multiplying the two differences together and then summing those. Our slope is then our sum of cross products divided by our sum of squares for X. And our intercept A is calculated by the mean of Y, so the mean of all Y values minus the slope times the mean of X. You don't need to know how to calculate these things for the exam, but again, good to know where these numbers are coming from. So when we're finding our best fit line, we're really trying to reduce the amount of variation unexplained by our X variable. So we're trying to figure out a line that best explains the spread of data. We do this by partitioning our Y variance, the variance in our Y variable, SS total, so sum of squares total, or SSY, to determine how much variation in Y is explained by the regression. So sum of squares regression is the variance explained by the regression. Sum of squares error / sum of squares residual, you can call them either, is the leftover. It's the residual sum of squares, the variance that can't be explained using our regression line. We don't know why there's that much variation still there. So our sum of squares total for Y, or sum of squares total / sum of squares Y, is each individual Y minus the mean for Y squared. The sum of squares for the regression is Y hat. This hat means estimate. So it's our best estimate of Y for each point minus the mean squared. And we calculate that by our slope squared times our sum of squares for X. The sum of squares error or residual is therefore just everything that's left over. It's our sum of squares total minus our sum of squares regression. And it's the difference between each point and our estimate of each point. And here are those described graphically. So sum of squares total is the variation between each y value and the mean of y. So each point and the mean of y, which is that red line. Our sum of squares regression is the variation between the mean of y and the estimate of y from our regression, so our best fit line. We're trying to reduce the variation between the mean and our best fit line. And then finally, we have the variation between each y value and the estimated y from the regression line. So we've got each point to the mean to our best fit line, and each point to our best fit line. And that's also where we get something called residuals from, which I'll explain in a little bit. But residuals, like that term residual, literally just means like leftover variation. Just like with the ANOVA, each of our sum of squares has its own degrees of freedom. For the regression, it's 1. For error or residual, it's n minus 2. And for total, it's n minus 1. We then have a variable called our coefficient of determination, which is our capital R squared. And this describes the proportion of variation in y explained by the variation in x. So all of that stuff about the sum of squares, I'm not testing you on. You don't really need to know that for this class, for this lab at least, this semester. But you do need to know about the coefficient of determination. So it's the proportion of variation in y explained by the variation of x. So it is a proportion. And is calculated by dividing the sum of squares regression by the sum of squares total. So in other words, the variation explained by our regression by the total variation. Right? If more variation is explained by the regression, it gets closer to the sum of squares total, right? If like literally like 90% out of 100%, right? If 90% of our data is explained by the regression compared to like the total, right? Total is 1 or 100%. That means that our R squared is like 0.9. So I'm just trying to say that the more variation that is explained by the regression, the higher your R squared is, because it gets closer to the total. So R squared will range between 0 and 1, 0% to 100%. There's also a direct relationship between little r, the coefficient of correlation, which we'll talk about when we talk about correlation in a second, and capital R squared, because R squared is just equal to R squared. When we're trying to determine significance, so whether our slope really is not 0, if it actually is something other than 0 and there is a significant relationship between x and y, we can test this one of two ways. We can test it using an ANOVA or a one-sample t-test. Using the ANOVA method, it's easy to calculate an R square. We get the same procedure, and it's the same procedure as a general ANOVA test. When we do our t-test method, we can test a one-tailed alternatives and non-zero slopes and can create confidence intervals. This isn't super relevant for our class this semester. In the past, when we did everything from the beginning till the very end of the semester in both R and Excel. This was more relevant, but still good to know. Doing the ANOVA approach, you compare the variation explained by the regression to the variation unexplained by the regression, right? And that was kind of clear that we were setting up for something like that when we have a figure like this. When we have sum of squares and degrees of freedom, that definitely tells you that you're probably calculating a mean squares or like actual variances. So if our mean squares regression is greater than our mean squares error, that means that the regression explains a significant amount of the variation. So the variance explained is greater than the variance unexplained, meaning that we probably have a significant slope. Using the t-test approach is a little bit more flexible because you can have other options. You can say that we expect our slope to be less than or equal to, like less than 0 or greater than 0, so a significant positive or negative slope. You can also have a like a priori hypothesis you're comparing it to. So maybe we read a bunch of papers and we hypothesize that the slope of a line is going to be like 2. We can then test that as a null and alternative hypothesis, saying the null hypothesis is that the slope is 2, the alternative is that it is not. So the t-test approach is a little bit more flexible in that regard. When we do these regressions, there are a couple of different results that we can get. So one option is that we get non-significant results. Our best of fit line is pretty much has a slope of 0, and there's no relationship between x and y. The next alternatives are that we either have a positive or negative slope. So as x increases, so does y, or as x increases, y decreases. These may or may not be significant depending on what the spread of data around the regression line looks like, or how much variation is explained, right? If our points are like this, like just right on top of that line, it's probably a significant line. But let's say we've got something like this, where we do have this negative slope, but the spread is really kind of wide. For something like that, maybe you won't, the slope is negative, but it's non-significant. We can also calculate confidence intervals for our lines. Again, this isn't something that you're going to be doing for your homework assignment or for the exam next week. But essentially, this equation for confidence interval should look familiar. So we've got our slope plus or minus our t critical value times the standard error for B. And this confidence interval pretty much creates bands around our line. So let's say this is our line, and then we've got kind of an interval around our line where we're like, we're 90% sure or 95% sure that the actual line for this population is somewhere between those 2 points or between those 2 bounds. Residuals, again, are just leftover variation that we cannot explain using our regression. And we actually use our residuals to check the assumptions, or check assumption 3 for the regressions, that the variation in y is normally distributed around the best fit line. And you can also use residuals to identify outliers in the data. So our residuals are calculated by comparing each point to our estimate of or each y to our estimate of y, or our best fit line. When you're looking at the residuals, you want to see a random distribution. Clumping is a bad sign. And residuals are literally, so you take your best fit line, you calculate the residual, the leftover variation, and then you rotate that line so that it's flat. And if you look at a plot of residuals, this is what you get. You have 0 in the middle. So if your point is sitting right on that line, it means there's no variation. If it's above the line, it means there's a positive variation. If it's below the line, it means there's a negative variation. So when we do regressions, we want to plot the data to check for a linear relationship. We want to test whether the slope is equal to 0. We're going to evaluate the fit of the regression using r-squared and residuals. And we're going to come to a conclusion referring to the equation of the line, the r-squared, and the residuals. And actually, we're not going to worry about the residuals for this semester. So you're going to look at your equation, your r-squared, and the p-value for your line. Next, we have correlation. So here's just a fun figure. So we have marriage rate in New York that correlates with murders by blunt object. And this is from 1999 to 2010. And they kind of eerily correlate with each other. And there's like a bunch of things like this. I think you can look up, I think there's a website that just has weird correlations like this. The point that I'm trying to make, though, is that correlation does not equal causation. Just because marriage rate and murders by blunt object kind of weirdly follow each other doesn't mean that marriage causes murder by blunt object, or that murder by blunt object causes marriages. So that's the key difference between correlation and causation. When we do our correlations, our null hypothesis is simply that there is no correlation between our independent and our dependent variables. We have this kind of p-looking thing, which is rho and r. So if our null hypothesis is then that rho, or r, is equal to 0, the correlation coefficient is 0. There is no correlation between x and y. The alternative is then that there is some sort of correlation between x and y. So rho, or r, does not equal 0. We actually use a one-sample t-test to test this. So our t-calc is equal to our r divided by the square root of 1 minus r squared over n minus 2. Where r is the sample correlation coefficient, which measures the strength of relationships between two dependent variables. And we calculate r by our sum of cross products divided by the square root of our sum of squares for x times our sum of squares for y. R actually varies between -1 and +1. The higher the absolute value of R is, so if it's -0.8, the absolute value is 0.8. So the higher the absolute value of R is, the stronger the linear relationship between the two variables. The positive and negative sign just indicates slope. A plus or a positive R means a positive slope, and negative R means a negative slope. 0 would be that there is no relationship between the two variables. So here we've got R equals, in the top right corner, we've got R equals, oops, where is my cursor? There it is. R is equal to 0.29. So there's kind of a correlation between, there's a somewhat positive correlation between X and Y. Here we've got 0.44. So there is a stronger, but still not super strong correlation between X and Y, and it is positive. Here R equals 0.9. So now we have a positive and kind of strong correlation between X and Y. And then in the bottom right, we've got negative 0.48. So now we have a kind of strong-ish, like a moderately strong, somewhat there correlation that is negative between X and Y. When we do correlations, we plot the data to see if there is a relationship. Is it linear? Should we even do a regression or a correlation? Calculate your R, your correlation coefficient, and get a p-value, and then come to a conclusion. So discuss the directionality of the relationship as well as the R and p-value. When we do correlations, however, there is no line of best fit. Remember, a line of best fit kind of suggests a causal relationship between X and Y. So for correlations, no line of best fit. Okay. So that's everything. There's some extra slides here, but they're like a problem that, again, isn't super relevant for the outputs because it's all in Excel, but they're still there if you want to look over them. Okay, so quick pause. I got to run to the bathroom, and then we'll get into all of the R stuff for today. Okay. Sorry about that. Are there any questions about the regression correlation or, yeah, any of that? Like I said, I'm not gonna test you on any of the sum of squares stuff. Really any of the like kind of detailed stuff about how it's all calculated. Really just doing it in R and interpreting the results. Okay. All right, so let's switch gears into R Studio. Okay. So when you're doing these, the first thing you want to decide really, so even before you plot your data or any of that stuff, is to determine whether or not you're doing a regression or a correlation. If you're doing a regression, the relationship between the two variables is being controlled somehow. The X variable is being controlled. That means that you have a true X and a true Y, a true explanatory and a true response variable. If you're doing a correlation, no variables are being controlled. They're just being measured. Remember, it's an observational study, meaning that there isn't really a true X or a true Y. There isn't a dependent or independent variable. We're just seeing, do they vary together? So again, our hypotheses for the regression are that the slope for the null hypothesis is that our slope B does not or equals 0, meaning there is no relationship between X and Y. Our alternative is that the slope is not equal to 0. It's either greater than 0 or less than 0, meaning there is a relationship between X and Y. Our correlation hypothesis for the null is that the correlation coefficient, core or R or rho, is equal to 0, meaning there is no association between X and Y. Our alternative is that our correlation coefficient does not equal 0, meaning there is an interaction or an association between X and Y. So when we do a regression, you have to create your model. And we create our model in a really similar way to how we've done most things at this point. But the new function we're going to use is this LM. And I think this is the one, I think there's only two new functions that we're using, is LM and abline, which we'll see in a second. So LM creates a linear model. And we use dependent, the little squiggly tilde again, independent, data equals data. And I meant for this to be .lm to keep it all consistent. So we are creating a linear model for our data. Similar to when we did ANOVAs, just doing this creates the model or the model object, but we can't actually see the results of it until we look at it using the summary function. When you use the summary function, you get a bunch of information. The things you want to pull out when doing a regression is your p-value, your r-squared, and the equation of your line. So if our p-value is less than 0.05, that means our slope is not equal to 0 and there is a relationship. If it's greater than 0.05, the slope is 0 and there is no relationship between x and y. The r-squared, the coefficient of determination, is the percentage of data that is explained by the model, by the equation. It's a measurement of how good your model is at explaining the variation in the data, and it also tells you how close the points are to your line. Your equation is y equals mx plus b, or y equals a plus bx, where you will need to find the slope, which is confusingly m or b, and the intercept is b/a, depending on which of these equations you're kind of following. So you need to find the slope and you need to find the intercept, and I'll show you where those are. The last thing you want to do is plot your data. It's kind of weird. You can start with a plot to make sure that your data are linear. That's the reason that you want to plot your data first and see if the variances are good. But let's see. Sorry, I'm trying to think this through. I don't think. No, actually, I will say, I plot your data first, make sure that it's linear. No, actually, never mind. Sorry. Don't worry about plotting your data first. You can plot it first. I was just trying to decide whether or not I'm going to give you any problems where you need to transform your data, but I don't think I will. So your data will always have either like no relationship or a linear one, you won't have to worry about transforming your data first. So yeah, plotting your data first isn't that a huge concern. Regardless, when you do plot your data, you're going to make a scatter plot with the regression line using this plot function. So you can do plot for dependent, squiggle, independent. Remember, dependent has to come first, comma, data equals the name of your data set. And if you do just this top portion by itself, you'll get a scatter plot. If you want to include a line, you need to include this plus, and then ab line, and the name of your linear model. And that will draw a line through your data points. When we're doing the regressions, it's actually only 2 steps. It's pretty quick. So you want to do your correlation test. And it has a slightly different code structure than what we've learned in the past. So we're using this core test function. We're doing data $ our X column, data $ our Y column. If you tried to do the X comma Y or X squiggle Y data equals the name of the data, it won't work. So this is the alternative to doing that. And just for your information, I guess, you can actually use this format, this data $ column name for any of these, for everything that we've done before. If you wanted to do like data $data, data $independent, and then ignore this part right here, you can absolutely do that. Truthfully, that's how I usually code stuff, because then you don't have to type the column names. But one of the other TAs who like does a lot of the writing for this, we both write them and everything, but like she does a lot of, she does like a little bit more of it. This is how she prefers to do it. So that's the way I've taught it to you for this class. But I typically do most of my coding with this format. You get a little bit fewer typos that way, in my opinion, but that's up to you. But for the core test function, you do have to do it this way. When you do this function, the outputs that you get are a p-value. You get a bunch of stuff, but the stuff that you need to pull out of it is your p-value again. Is it less than or greater than 0.05? If it's less than 0.05, your correlation coefficient does not equal 0, and the variables are associated with one another. If your p-value is greater than 0.05, your correlation coefficient is equal to 0, and your variables are not associated. Your R, or correlation coefficient, again, remember, it tells you how close the association is and in what direction, because you can get a negative or a positive correlation coefficient. This kind of breakdown is somewhat arbitrary, but this is what we're going to go for to make things a little bit easier to interpret. If your correlation coefficient, if the absolute value is greater than 0.8, your variables are strongly correlated in a positive or negative way, depending on whether this number was negative 0.8 or positive 0.8. If it's somewhere between 0.6 and 0.8, your variables are marginally or somewhat correlated in a positive or negative manner. If the absolute value is less than 0.5, then your variables are weakly correlated. Or if it's, very small and your p-value is greater than 0.05, it means your variables aren't correlated at all. You don't have to pull out an equation because this is a correlation and we don't have a regression line. We didn't control for any variables to have the power to say that X causes Y. You can then plot your data as the same way as up here, dependent. Well, it's not dependent, independent, remember, because there is no independent and dependent variable. So that's why it's written as variable 1 and variable 2. Data equals the name of your data set. Remember, because there is no true X or Y. Okay, so let's try some of those. I think it will be a little clearer that way. So let's check out the data. So we had our warm up, and now we're doing example 1. We have light exposure and photo rate. So light exposure and photo rate are the two that we're looking at right now. So these columns are from an experiment where we controlled light exposure to a plant to see how photosynthetic rate would respond. Is this a regression or a correlation? This is a regression because we are controlling for a variable to see how the dependent variable responds. So because this is a regression, that means that we're looking at our slope. We want to know, is our slope significant? So B or M or slope, however you want to write it, the null hypothesis is that it is equal to 0. There is no relationship between between light exposure and photosynthetic rate. Your alternative is that the slope, B or M, or the slope, is not equal to 0, meaning there is a relationship between light exposure and photosynthetic rate. Or light exposure causes a change in photosynthetic rate. All right, so actually doing the analysis. Let's go ahead and create our model, typing in what I have here. So we need to make our model using the LM function, the linear model function, and then we need to view the results using the summary. Remember, you should type it, get it into your muscle memory. It'll be better for you when you're doing the exam, but if you do copy it, don't copy these little tick marks. Those are just a formatting thing. So our linear model for light exposure versus, because that's our dependent variable. So we're saying, oh wait, I think those, yeah, these are backwards. This should be photo rate. Yeah, is photo, because we want dependent and then independent. So is our photosynthetic rate affected by our light exposure? Data equals chapter 19. And just to show you what I meant before, if you did it as chapter 19, $, you could do photo rate. And remember, like, what I like about this is that you do chapter 19, $, and then you can tab through this. Highlight photo rate, hit the tab key. Squiggle, chapter 19, $, scroll down to light exposure, hit the tab key, and that's it. And it's a little bit less typing, a little bit less likely to make errors, but again, totally up to you which method you want to use. And then summary of our example 1 linear model, which isn't created yet. I typed everything out, but I'm going to go ahead and run them all together. Control Shift Enter. And we've got, oh, the formula up here is using the second one here. I can name it something else so that we have all of them. So we've got, so this is our output. It gives us the formula that went in, our residuals, and our coefficients. This is what we're really going to be focusing on, is our coefficients and our multiple r squared. Ignore, we're not going to use the adjusted r squared. We're going to use the multiple r squared. So what we find is, I think I have some of these written backwards. Okay, so we've got our right photo rate. Yes, I think this is right. Okay, sorry, there were some typos in the original file that I was fixing late last night. Let me just, I think that I fixed them. I think that I fixed them correctly. Let me just switch these around for a second and double check. Yeah, okay. Okay, so ignore that. Everything is fine. I think that there are still some typos, but it's fine. Okay, so the results are for our line, right? So let's go through the things that we want to pull out for this. We want to pull out our line, so our equation. We want our p-value, but we also want our r squared value. So our equation is, if we do the y equals mx plus b version that most people are familiar with, our slope is right here. So we've got coefficients. Let's read through this. We've got coefficients, we've got intercept, and we've got light exposure. We have our estimate, our standard error, our t-value, and our probability that it is greater than the absolute value of t. So this column at the very end is our p-value. We've got the t, standard error. The estimate is our actual slope and intercept. Intercept is intercept. So this is the estimate of the intercept. This is our estimate of our slope, 0.7213. And I'm just going to copy it actually. So that is our slope, our estimate for our slope, plus the estimate for our intercept. So our equation for our line is y equals 0.7213x plus 7.02820. Our p-value, and there's two p-values. So you have a p-value for your intercept, and you have a p-value for your slope. The p-value we're focusing on is our p-value for our slope. Remember, that's what our hypothesis is about. Is our slope equal to 0 or not? So we're looking at the p-value for our slope, which is less than 0.05, meaning that we're going to reject our null hypothesis that there is a relationship between x and y. Finally, we want to pull out this r squared value. Again, multiple r squared, not the adjusted r squared. Our r squared value is this 0.7213. So kind of by chance, it's also the same thing as our slope. So those are the pieces of information you want out of the output for your linear model. So let's go through the discussion. So our R squared is 0.72, so it's kind of high. The data marginally fits the model, or somewhat well fits the model, and there's a little bit of variation still around the data. We can say that an increase in light exposure likely caused an increase in photosynthetic rate. But let's look at the figure actually and see to make that relationship a little bit clearer. So let's plot our data using the plot function. Remember our dependent variable first, so photo rate by light exposure data equals chapter 19. Plus, you need to include that plus at the end. And when you hit enter, it'll give you this little tab, and that just kind of indicates that the line is continuing. Ab line, and then our model, example 1 linear model. And now we can actually visualize that relationship that we were just talking about. So we still got some spread of data, right? Our line isn't really actually touching any of the points. It's going straight through them. It is positive, which we can see by the slope we got. Our intercept is at 7, which we can't even actually see, it's cut off. But yeah, our slope is significantly positive, and we have a somewhat or moderately well-fitting model. The abline function puts the line on there. So if you do it without that, so plot if you plot it without it, you just get a scatter plot. Because this is a regression, you need to have a line. If this problem was a correlation, you wouldn't do the abline. So for example 2, we're going to use the same data set. So still using light exposure and photo rate. But this time we're going to kind of imagine a situation in which we actually went into the field and recorded this data. So the light levels, so we went to a field and recorded the light levels on a given day, as well as the photosynthetic rate of plants. So not an experiment that we're doing in the lab. This means that this should be a correlation because we didn't control for either variable. So same data, different situation in which the data was collected, making it a different test. When we do a correlation, we're checking to see if our correlation coefficient, core or R or rho, is equal to 0 for our null hypothesis. If our correlation coefficient is equal to 0, that means that there is no association between light exposure and photosynthetic rate. If our correlation coefficient /r/rho does not equal 0, that means there is an association between light exposure and photosynthetic rate. These are really similar hypotheses to what we had up here, but I can't include this extra bit. This light exposure causes a change in photosynthetic rate because I didn't control light exposure. They were both just collected, and I have no way to say that light exposure causes a change in photosynthetic rate. When we do our analysis for this, we're going to use the core test function, core.test. And for this one, you don't have any option. You have to do chapter 19 $. You have to do it this way. If you do it the other ways, you get an error message. So chapter 19 $, photo rate, and then I just hit the tab key. Remember, when they're highlighted, you can hit tab and it just fills all the way out. So we get a Pearson correlation rate. So we get our t-calc, degrees of freedom, our p-value, which is less than 0.05. We actually get a confidence interval for our for a correlation coefficient and our correlation coefficient. So the data that we want to pull out when we're doing a correlation is just our p-value and our correlation coefficient. So our p-value is less than 0.05, so we reject the null hypothesis. Light levels and photosynthetic rates are associated with each other. Our correlation coefficient is 0.849, right? 0.8493006, which means that we have a high positive correlation, or R or rho, or not rho, core or R. It's because it's just a sample. Meaning that light levels and photosynthetic rates are strongly correlated in a positive manner. Because remember, correlation coefficients can be negative or positive, and the negative or positive indicates slope. But because this is a correlation, we can't say that the increase in light levels cause a change in photosynthetic rates. They're just correlated. So when we plot our data, we don't include a line because the line suggests causation. So plot photo rate by light exposure data equals chapter 19. And you could actually also, again, up to you, do it this way as well. Oh, I always forget about that. If you use the comma, though, it switches the order of them. It's like a weird thing. Except the downside to that is that you get these really ugly like axis labels. But just showing you both of them work. And we see the same thing that we saw when we did up here, except now we don't have a line because we didn't include the appline function. Cool. Are there any questions about that? Cool. Yeah, I feel like it's really nice to kind of end the class with correlation and regression because they're not super difficult. Most people have used lines at some point. But yeah. Okay, so we're going to do a little bit of group data collection. This one will be super fast because you don't actually have to measure anything. You just have to do a couple of conversions. So we're going to see how height and shoe size vary. So I'm going to give you a Google sheet where you're going to enter your height in inches and your shoe size in inches. And we're going to check out the data with that. So let me get that together. Or I guess this is really like height versus foot size, but or foot length, but what? I think the way we had this set up before, it was, I don't know. You needed to like measure a bunch of stuff, and I was like, people probably don't really have rulers laying around. I don't know. So hopefully this works fine. Okay. So I just sent everybody the link to edit. So go ahead, do those conversions. Thankfully, this will be pretty simple. Just put it down wherever. Make sure you're using inches. Yeah, we'll just use inches. That's fine. And when you are finished, go ahead and click off of the sheet or close it so I can tell when we're done. And while you wait, go ahead and take a look at some of the practice problems. Okay. It is all set up. If you want, you can click back on and download it as a CSV, or you can wait for me to post it to Beachboard. Okay, it's up on Beachboard, so go ahead and download that. Okay. So file choose or upload if you're still using RStudio Cloud. It's just the height versus foot 09B. Okay. So copy that and paste that in and check out the data. Okay. So when we look at our data, we see our height and our foot length. So are we going to be doing a regression or a correlation?
Would it be a regression? I mean, a correlation.
Yes, yeah, it's a correlation because we're not controlling our height or our foot size, right? So this is purely observational data. So this is a correlation because nothing is being controlled. So since it's a correlation, what are our hypotheses about? Are we looking at our slope or are we looking at our coefficient? Yeah, we're looking at our correlation coefficient. So core or R, whichever you want to say it as, is equal to 0 is our null hypothesis for all correlation coefficients or all correlations. And that our correlation coefficient is not equal to 0 is the alternative. Specifically for this problem, our null hypothesis would be that height and foot length are not significantly associated. Our alternative is then height and foot length are significantly associated. The analysis is pretty short and sweet, right? Just the core.test function. We have to remember that we're doing, oh, what did I say that as? Length. So length, $sign, remember you have to do it in this format. And then it doesn't matter which one we pick because neither is specifically independent or dependent, right? So length, $sign, foot, we're just comparing the two of them. We run that, we get our p-value, which is very significant, and our correlation coefficient. So the outputs, equation if it applies, which it doesn't in this case, we only use an equation when we're doing a regression. R squared, our coefficient of determination, again, doesn't apply because we only use it when we do our regression. So that's just our correlation coefficient, which does apply in this case. And our coefficient, you can just copy it and paste it down there. And our p-value for our correlation coefficient is up here. So a pretty high correlation coefficient, a very small p-value, so definitely a significant positive correlation between the two variables. Let's actually look at our data and see what we have. So we're plotting again, and because height doesn't cause foot and foot doesn't cause height. It doesn't matter which way we do it. So I'm going to do height on the x-axis and then foot, I guess, on the y-axis. So height and foot data equals length. And there we go. So we actually see that we maybe have a little bit of a non-linear relationship here, right? There's like kind of, it's not really a straight line. There's like a bit of a curve to it. It's probably more of like a logarithmic relationship technically, where it goes up and then it kind of tapers out and across. So a linear model, like a regression or correlation, probably isn't quite the best fit for this data. Another option to see if it fits a little bit better would be to transform our data first and then see, which, like I mentioned before, I'm not going to have you do, but kind of just for fun, I'm going to go ahead and do it and transform it just as an extra step. So see, just some bonus. Transforming the data so it's more linear. These are both continuous, so we're actually going to transform both axes. So let's do log foot, log of length, $, foot. And like I said, I'm not going to have you do this for your exam. So if you want to do this as well and like follow along, you absolutely can, but don't worry if I'm going fast and you're having a little bit of difficulty keeping up. So we're transforming them. Now we can do the correlation again. So core.test, and then because we created 2 new objects, we don't even actually have to use the chapter 19 because there are no columns called log foot or log height in the chapter 9, or not the chapter 19 data, the length data. So it's really just log foot versus log height. It looks like our p-value is a little bit smaller, or a little bit bigger actually. It's like a little bit worse. And our correlation is actually a little bit worse as well. So, or is it? Is it? It's like slightly better, barely, like barely, barely. Let's see what that actually did for the data for the plot. Yeah, it kind of like, oh, I think I switched them. That's probably why. But that looks weird too. Yeah, so that didn't really do anything. Maybe if we just log transformed one of them. Which one has the biggest outlier? Maybe if we just log transform height and not foot. Sorry, I'm just kind of wondering now. Oh, that's why. Yeah, that didn't really do it either, so never mind. But those are some options. Again, I'm not going to have you transforming any of the data though to make it more linear, so don't worry about it. But yeah, so that's actually it. We still have 45 minutes left. There's some practice problems for you to go through with your group. but I will kind of do a quick survey for some options that we can go over. Do you want me to do another problem as an example? Kind of option one. Option here, maybe I'll actually type these out so that it's kind of clear. Option one, extra examples. Extra examples. Number two, review for exam. And then I'm almost positive you're not gonna pick this. Breakout groups. So what do people want to do for the next little bit of time? And we can do more than one of these. Okay. Okay, cool. So yeah, we can go over the review for the exam. I posted a review PowerPoint that we can go through now. I also posted, let's see. Okay, let's see. So, and I can unhide these. So you don't have any other homework assignments. You're done with homework. Underneath of lab 12, you have a lab 2 exam section now. And I have this tab visible to you for review materials. So the lab exam 2 review is the PowerPoint. We can go through that now. There's also a kind of like a template. Sorry. There's a template for you to like answer the study guide and practice problems, like an R markdown template for you to work through everything. The study guide, so exam 2 study guide has practice problems for you to go through. And each of these is the individual CSV file for each of those. And then the practice problems is set up in the same way. There's a practice problem. Oh, wait. Okay, this isn't. Okay, this is actually fine. So there's also a practice problem thing up for you. The only one you don't really, oh no, this one is fine too, actually. So yeah, there's these practice problems, and again, an individual CSV file for each of the practice problems. But yeah, we can go over the PowerPoint now. See, the final exam, let's see, Henry, do you mean like, is it going to be at a different time, or is it going to take a different like amount of time? It's
Yeah.
gonna be, sorry, what?
Like is it gonna be like the same class time, or is it gonna be like from 10 to 12 or like
No,
something?
it's gonna be the same class time. It's the same thing as when we did the exam 1.
Okay.
So it'll be next week starting at 9 a.m. for the entire class period.
Okay, got it.
Yeah. The exam is also going to be structured the same way as exam 2, or sorry, exam 1, where you'll go to like the quizzes section and all of the problems will be like written up in the exam, but I'll provide you with the CSV files as well as like an R markdown kind of structure for you to follow through.
Okay, sounds pretty clear.
Yeah, so, and then you'll just submit the R markdown and I will grade that. Same thing as when we did exam 1 and you submitted the Excel file and I just graded that. So the quiz questions will be, again, true or false. The answer is true, but that's not what I'll be looking at.
Okay, cool. Thank you.
Yep, no problem. Okay, so let's check out the review. So lab exam 2 covers everything since lab exam 1. So that's chi-squared tests, 2 sample t-tests, 1-factor ANOVAs, 2-factor ANOVAs, and then regression correlation. So 5 topics. So for the 2 sample t-test, remember that you have group 1 versus group 2, and you're comparing means. And you're saying, is the mean of group 1 different from the mean of group 2? These could be paired before and after kind of studies. They can be different species. They can be different treatments. Like one species, but one was fed oats and the other was fed corn for a month, and see how weight changes. It could be, species 1 versus species 2. So 2 groups, the numbers, like the types of measurements are the same, and you're comparing the means. When you're doing these tests, there's a couple of questions you want to ask yourself. Step 1, are the data paired in any way? If they are, you're just going to do a paired t-test, and that's kind of where it ends. If the answer is no, you have to check if your data has equal variance. If it does, you're going to do a homoscedastic t-test. If it doesn't, you're going to do a heteroscedastic t-test. You don't want to forget that the default code for a t-test in R, the t.test code, automatically does a 2-tailed, unpaired, heteroscedastic t-test. If your test is paired, you have to specify that. If your test is homoscedastic, you have to specify that. If your tail is one-tailed, you need to specify that. Your hypotheses can be 1 or 2-tailed, remember? So your null hypothesis could be that for a 2-tailed test is that the mean of group A is equal to the mean of group B. The alternative is the mean of group A is not equal to the mean of group B. For the 1-tailed hypotheses, it'd be group A is bigger than group B, or group B is bigger than group A. And remember that there always has to be some sort of equal sign in your null hypothesis. If you have any questions at any point during this, like either shout them out or put them in the chat. I'm like keeping an eye on that. The things that you want to report and that I might ask you about are your p-value, your t-critical or t-calc. I probably won't ask you about that, but I could. So keep an eye on your t-crit, t-calc. And whether or not you reject the null hypothesis. That's really key, right? Is your p-value less than 0.05? Is it greater than 0.05? Do you accept or do you reject? Are the means different from each other? How are they different from each other? For our chi-squared tests, we have one number in each category. We have categories 1, 2, and 3, and we have groups across as well, category A, B. And we're looking at these combinations. So A1, B1, A2, B2, A3, B3. We're seeing if there's any sort of interaction, essentially, between the 2 categories. And there's a couple of different types of chi-square tests. Remember, there's goodness of fit, independence, and homogeneity. When you're doing goodness of fit, that means that there's some implied distribution, whether that's binomial, Poisson, or like a Mendelian segregation one. There were a lot of people who had issues with the Mendelian genetics, so I recommend definitely review that before the exam. For independence, you have two traits in one population, and you're trying to see, does trait 1 or trait 2, are they independent from each other? For homogeneity, you have one trait in two groups, and you're seeing, is the trait homogeneously distributed across the populations? And don't forget, for these two, you use a CSV. For this one, you have to make a matrix. Oh, wait. No, you don't. For this one, sorry, for this one, you have a CSV that you need to make a matrix out of. And for this one, you enter your data. Remember, you make your expected and your observed. There aren't any assumptions for the chi-square test that you need to check. And there are 3 hypotheses. Remember, the base hypothesis is always the same, that your observed is equal to your expected frequency and that your observed frequency is not equal to your expected frequency. That's the same regardless of what test you're doing. What differs is how you interpret the results. For the goodness of fit, which is this top one, if you accept the null hypothesis, that means that your data fits the expected distribution. Your data fits the Mendelian segregation. Your data fits the binomial distribution. Your data fits the Poisson distribution. Your data fits a uniform distribution. The alternative is then that it doesn't match the distribution. Your data is distributed in some other way. For independence, you interpret your null and alternative as your traits are independent for your null, or your traits are not independent for your alternative. For homogeneity, your null is that your traits are homogeneous. Your alternative is that they are not. And remember to be careful because these two can look very, very similar to each other. The data looks similar, the way that you do them looks similar, the outputs are the same. It's all about, was it 2 traits in one population or one population with 2 traits? Sorry, I meant to delete this homogeneity part. For the chi-squared test, in your discussion, you're going to give the p-value. I might ask you about your chi-squared calc and your expected proportions. And remember that you can get your expected proportions. Sorry. By using your chi-squared object. So the name dot chi, remember you have to make your chi-squared object, $ expected. And that will give you your expected proportions. For the one factor ANOVA, the data has multiple numbers belonging to each category. And there's only one factor, right? So category 1, 2, and 3, but they're all from like the same kind of factor. So could be light level, could be nutrients, could be season or location, stuff like that. So only one factor. All of the numbers here are for the same type of measurement in the same units. It's essentially like a t-test, like a 2-sample t-test, but 3 samples or 4 samples or 5 samples instead. We always assume equal variance. Unlike the t-test, which if we have unequal variances, we just do a heteroscedastic t-test. When we do the ANOVA, your data has to have equal variances to do the ANOVA. If your p-value is greater than 0.05 when you test your equal variances using the Bartlett test, that means you have equal variances and you can do it. If your p-value is less than 0.05, you reject your null hypothesis that your variances are equal, meaning before doing your ANOVA, you have to transform your data. Remember, if it's, let's see, continuous, sorry, I'm writing at a really weird angle. Continuous, you do a log. If it's discrete, you do a square root. Your hypotheses, oh, and this should be or less than, is that your variance among is less than or equal to the variance within. So the mean dependent variable will not be different by the factor. Your alternative is that your variance among is greater than your variance within, and the mean dependent variable will be different by the factor. Essentially, your means are different between the groups, or your means aren't different between the groups. For the discussion, the things I might ask you are whether the factor influences the mean. So going back to your p-value, which was significant, describing where the differences are occurring between the factors from the Tukey test, and describing how they're different using the graph. Is one group's mean bigger than another group's mean? Are group A and group B about the same, but they're both smaller than group C? Stuff like that. The 2-factor ANOVA should be pretty fresh. So your data has multiple numbers belonging to 2 categories. So now we have factors A, B, and C, but we also have factors 1, 2, and 3. And we have numbers for each of those combinations. So we have A1, B1, C1, and we're calculating the means of each of these combinations. Oops. You guys get it. You know what I'm trying to do. Just like the 1-factor ANOVA, we assume that we have equal variances. Variance has to be equal by both factors. So you need to check using the Bartlett test for each factor. So dependent variable by factor 1, dependent variable by factor 2. If one of the p-values is less than 0.05 or both, you need to transform the data. If both p-values are greater than 0.05, you can continue with the ANOVA. Your hypotheses, again, are the same for the 1-factor ANOVA. Your null is that the variance among or between is less than or equal to the variance within. And this just tells you the mean dependent variable will not differ by factor 1 or factor 2, and there is no interaction. The alternative is that the variance among or between is bigger than the variance within. The mean dependent variable will differ by factor 1 or factor 2, or there is an interaction between them. Just one of those things has to be occurring to reject the null hypothesis. Sorry, and this should be a 2-factor ANOVA. So state whether the factors influence the mean. So looking at the ANOVA table, what are your p-values? Is factor 1, factor 2? Is there an interaction maybe? Describe where the differences are occurring within the factors using the Tukey test. Describe how they're different looking at the graph, and also determine what the interaction is from looking at the graph. Is there an interaction or not, and how and what might be the interaction? How are the different combinations of factors affecting the response variable? For your regression, you have 2 columns of numbers for 2 different variables. Both of them are continuous. You are controlling for the independent variable to see how the dependent variable responds. There are assumptions, but there are none that we check for in this class. Your hypothesis is that your slope mb beta is equal to 0. And there is no relationship between x and y. That's your null hypothesis. Your alternative hypothesis is that your slope mb beta is not equal to 0. There is some sort of relationship, positive or negative, between x and y. For your discussion, you're going to tell me what your p-value is. You're going to tell me what your r squared is, and the equation of the line. You have to pull out all of this information from the output of the regression when you do the summary function. So if the data is related, describe how it's related, looking at the graph and or the equation. And tell me how well the data is, tell me about the dispersion of the data. So your R, and that's where you'll get from your R squared value. If it's a really high R squared value, that means that there's very little residual variation unexplained by the regression. If it's a really low R squared value, even if your p-value is small, even if your regression is significant and your R squared value is low, that means that there is a significant relationship, but the line of best fit isn't maybe the best way to describe the relationship. For a correlation, there are, another typo should be data. There are 2 columns of numbers, no independent variable. No dependent variable really either. It's just variable 1, variable 2, because nothing is being controlled for. So nothing is independent or dependent on anything else. So, and I believe this is like the same data as the regression. It's just one is being controlled and the other is not. But for the correlation, neither is being controlled. So you're just observing data. It is not an experiment. Again, there are assumptions, but none that we're testing for. Our hypotheses are that our correlation coefficient R or rho is equal to 0 for our null hypothesis, meaning that there is no association between x and y. The alternative is then that our correlation coefficient is not equal to 0. There is an association between x and y. Some of the things I might ask you to talk about are your p-value, your R, your correlation coefficient, And there's no equation for these. So if there is a correlation, describe how the variables are correlated, positively or negatively. Your correlation coefficient will be positive or negative. You can also look at the graph to see how they're correlated. What's the spread of data like? Is it very close together? Is it really spread apart and dispersed? You can look at your correlation coefficient and your graph again to determine those things. Finally, for your exam, you are allowed a cheat sheet again. You get to use one full sheet of printer paper or, lined paper. That doesn't matter, but one full sheet of paper. So 8.5 by 11 inches. When you do this, you need to submit a picture of it. Even if you didn't really use one, even if you just wrote your name on it or something, yeah, so take a picture and submit that with your exam. You can also use your printer paper as your scratch paper, like on the other side. I want a picture of your scratch paper as well. I can see you when you're writing, when you're doing your exams, and I see you writing. I want a picture of what you've been writing down, as well as your cheat sheet. So the kinds of things that you can include on your cheat sheet are R codes. So saying, data, $, factor, as factor, that kind of stuff to remember how to do everything. You can write down your hypotheses and how they're supposed to be worded. What important things are there about that? You can write down the outputs that you need to report for each test and kind of interpretations that need to be made. You are not allowed to include any worked examples with numbers that we've done in class. Okay. Are there any questions about any of the review material, the cheat sheet, any of that stuff? Okay, cool. So so you don't have a homework assignment for this week. You're done with homework assignments. So you have no correlation and regression homework. But there are a bunch of correlation and regression practice problems that I'm going to put you in your breakout groups to work on now. And I really recommend, even if you don't finish them in the class time, the rest of the class time for today, that you do them so that you do get that extra practice that you would otherwise get doing a homework assignment. And then, yeah, also look at all the study guides and the practice questions that are posted on Beachboard. I will be holding office hours this week, Wednesday 12 to 1, Friday 12 to 1. I don't think I have anything in my schedule that's making that not happen. Oh, I will actually be moving my office hours for Wednesday. I will do my office hours on Wednesday. I'll do them earlier. I'll do them earlier and I'll hold them for longer in case the new times don't work for anyone. From let's do 9 to 11. Yeah. So Wednesday from 9. Sorry, I'm like changing that in my calendar right now. From 9 to 11. So for 2 hours, I will have office hours this coming Wednesday. And then Friday, regular time from 12 to 1, I will hold office hours. If you have any questions. Okay, but that's everything. Oh, do your spot evaluations. Please do your spot evaluations if you haven't already. I read everything that you write on that. If you have comments about how this class was done, about how things can be improved in the future. It's kind of weird because it's an online thing, but honestly, who knows how long this will be going on for. Make comments about that. Also remember though that Waylon's class isn't my class, and if you have issues with Waylon's class and how he's done things, put that on his spot evaluation. But if you have any comments, positive or negative, about how this class was done, please do those. Please write them down. Like I said, I read everything. And have made changes in accordance with things people have said in the past. So do those. But that's it. You guys did it. So a little round of applause to everyone. Thank you, Mia. That's really sweet. But yeah, way to go, everyone. This class is so hard. I know that it's so hard. There's a ton of information. We really cut back on a lot of the information that we usually test you on, and switching to entirely doing this in RStudio, or the second half in RStudio and the first half in Excel, I think made things better too, because before everything was taught both in R and in Excel, and it was too much. It was way too much. But yeah, oh, thank you everyone for all these sweet comments. That's really kind of you. But yeah, so thank you for being a great class. It's tough. I know it's tough. Thank you for sticking out through it. And I promise you, this stuff is really useful. It'll look great on your resume if you can tell people that you know how to do this. But yeah, okay. So sorry, you guys are making me a little emotional. This is so sweet. You guys are so nice. All right, I'm gonna put you in your breakout rooms for the last like 10 minutes or so to work on your practice problems and get in that extra correlation and regression practice. But all right. And you're free to go at 11:45. I've said everything I had to say. So have a great rest of your day. I will see you next week. Study, be prepared, make your cheat sheets. Don't forget your cheat sheets. A lot of people didn't have them last time. So